You are moving right now, not just spinning with the Earth or orbiting the Sun. You are falling through space at over 1,000,000 miles per hour, pulled by something so massive that it contains more galaxies than there are grains of sand on every beach on Earth, and you have never felt it. You have never seen it. Until now, you did not even know it had a name. This is not a black hole. It is not dark matter. It is not something hidden in the equations of physics, waiting to be proven. It is something we can see, something we have photographed, something that exists in the most ordinary way possible. It is simply there, in space, made of normal matter, galaxies, billions of them, arranged into a pattern so large that when you finally understand how large, something breaks in the way you think about the word thing. Because here is what they do not tell you about space. We talk about it being big. We say the universe is vast. We throw around numbers with so many zeros that they stop meaning anything. But there is a specific point where big stops being a useful word, where the brain does something strange. It stops trying to picture the thing and starts protecting you from the attempt. That point is somewhere around 10 billion light years. Let me tell you what that means without using the number. If you could move at the speed of light, the absolute speed limit of the universe, the fastest anything can possibly go, and you started moving the moment the Big Bang happened, you would still be traveling. You would not be halfway done. You would still be crossing this structure right now, 13.8 billion years later, still moving, still inside it. This is not a galaxy. Galaxies are small compared to this. This is not a galaxy cluster. Those are small too. This is not even a supercluster. This is something that makes superclusters look like pebbles on a beach. And the beach is bigger than anything your brain was built to contain. You live inside this beach. Right now, you are part of this structure, not metaphorically. Physically, the Milky Way, our galaxy, is connected through invisible threads of gravity to this thing. We are being pulled by it. We are flowing toward it. We are participants in something so enormous that the light showing us what it looks like has been traveling since before Earth existed. And here is the part that should disturb you. This structure is not special. It is not the only one. It is just the biggest one we have found so far, which means the universe builds things this large routinely, casually, without effort, as a natural consequence of physics acting over billions of years. We have been living inside a universe that constructs architecture on scales that make planets look like atoms. And we only just noticed. We only just looked up, collected enough data, processed enough light from enough galaxies, and realized, oh, there is a pattern. There is a structure. There is something so large that it redefines what the word large is allowed to mean. And once you see it, once you understand that it is real, you cannot unsee it. You cannot go back to thinking the universe is just stars scattered randomly in darkness, because it is not random. It is organized. It is connected. It is built. The largest structure we have ever discovered is not hiding in some distant corner of space. We are inside it, connected to it, part of it, and it has been there the entire time, waiting for us to become smart enough to see it. If this journey through the universe interests you, you can subscribe and continue exploring the quiet truths written across the cosmos. We need to start over, not with the structure itself, but with the idea of size. Because the problem is not that you do not know how large this structure is. The problem is that you do not know what large stops meaning when numbers become this extreme. Let us begin with something you can hold, a grain of sand. You can feel its edges. You can see where it ends. This is what an object is in human terms, a thing with boundaries, a thing you can encompass with your senses. Now imagine a beach. You cannot hold a beach. You cannot see all of it at once, but you can walk across it. You can understand it as a collection of grains. Your brain can still contain the concept. This is the furthest most people ever stretch the idea of large in a tactile sense. But the universe does not care about what your brain can contain. It builds at every scale available to physics, and physics allows for scales that are violent to human intuition. Here is the first place where intuition fails. Take that beach. Now multiply the number of grains of sand by a number so large that if you started counting them right now, 1 grain per second, you would still be counting long after the sun has died. Your brain cannot hold this, but you can still think many grains. You can still think beach, but more. Now forget the grains. Think about the beach as a single thing, a continuous surface. This is what happens when you zoom out far enough. The individual pieces stop mattering. You stop seeing sand and start seeing a smooth expanse. This is the first transformation of scale. Detail becomes texture. Texture becomes color. Color becomes a single point. This is what happens when you look at Earth from the moon. You do not see buildings anymore. You do not see trees. You see blue and white and brown. You see weather. You see a sphere. From Mars, Earth becomes a dot. A pale blue dot, yes, but still just a dot. All the detail is gone. Everything you think of as large, every mountain, every ocean, every continent, compressed into a single pixel of light. But we are still in the shallow end of scale. We have not even left the neighborhood yet. Our sun is large compared to Earth. You could fit over 1 million Earths inside the sun's volume. 1 million. And yet the sun is a medium-sized star. There are stars so large that if you placed one where our sun is, its surface would extend past the orbit of Jupiter. Stars so large that light takes hours to travel from one side to the other. And yet these giant stars are still just points of light when you step back far enough. They are still just objects. Things with edges. Things you could, in principle, travel around. But now we reach the place where something strange happens. We zoom out further, and instead of finding larger objects, we find that objects start to gather into patterns. They cluster. They form neighborhoods. And these neighborhoods themselves have structure. This is not intuitive. You would think that space, being so vast, would be mostly empty, with stars and galaxies scattered randomly like dust in a room. But that is not what we find. We find organization. We find architecture. Our sun is part of a galaxy, the Milky Way, a spiral of several 100 billion stars, all orbiting a common center, all held together by gravity into a disk shaped roughly 100,000 light years across. 100,000 light years. Let us pause there. A light year is the distance light travels in 1 year. Light moves at 299,792,4058 meters per second. In 1 year, it covers about 946 trillion kilometers. Our galaxy is 100,000 of these lengths across. If you wanted to drive across the Milky Way in a car, traveling at highway speed without ever stopping, it would take you about 1 trillion years. The universe is only about 13.8 billion years old. You would need the entire age of the universe 70 times over just to make the drive. And yet, from outside, from far enough away, the Milky Way is just a smudge, just a spiral of light. You could cover it with your thumb. Because there are larger structures still, the Milky Way is not alone. It is part of a small group of galaxies called the Local Group. About 50 galaxies total, most of them small dwarf galaxies, all loosely bound together by gravity. The Local Group spans about 10 million light years across. And the Local Group is part of something larger, a cluster of thousands of galaxies called the Virgo Cluster, about 55 million light years across. And the Virgo Cluster is part of something larger still, a supercluster, the Laniakea Supercluster, about 500 million light years across, containing roughly 100,000 galaxies. We are now at scales where even light, the fastest thing in the universe, takes 500 million years to cross from one side to the other. We are at scales where galaxies, each containing hundreds of billions of stars, are just the building blocks, just the atoms of a larger architecture. But we are still not at the largest structure. We are not even close, because something happened when astronomers started mapping the universe at these scales. They expected to find randomness. They expected to find galaxies distributed more or less evenly throughout space, with clusters here and there, but no overall pattern. What they found instead was a web. Not a metaphorical web, not a poetic description, an actual physical web-like structure spanning the entire observable universe. A cosmic web made of galaxies. Imagine you are looking at a 3-dimensional map of space. You plot every galaxy you can detect, billions of them. And when you connect the dots, when you let the data show you the pattern, You see something that looks biological. You see filaments, long, thin threads of galaxies stretching across hundreds of millions of light years. You see nodes where filaments intersect, creating dense clusters of galaxies. You see walls, vast sheets of galaxies forming surfaces in space. And between all of this, you see voids. Enormous empty regions where almost no galaxies exist at all. The universe, at its largest scale, is not a uniform distribution of matter. It is a foam, a sponge, a network. This was not predicted. This was discovered, and the discovery was disturbing because it meant the universe had organized itself in a way that required explanation. Something had carved out these voids. Something had pulled matter into these filaments and walls. Something had created structure at scales so large that even superclusters were just the building blocks. That something was gravity, but not recent gravity, ancient gravity. Gravity acting on tiny differences in density that existed when the universe was very young, just after the Big Bang. Regions that were slightly more dense than others attracted more matter. Regions that were slightly less dense became voids. And over billions of years, these tiny differences grew into the cosmic web we see today. This is important to understand because the largest structure we have discovered is not separate from this web. It is part of the web. It is an element of the web so large that it challenges our definition of what a single structure can be. But before we name it, before we describe it, we need to understand what it means for something to be a structure at this scale. When you look at a building, you know it is a structure because it was designed, because someone built it with intention. It has a purpose. It has internal coherence. The parts work together. When you look at a mountain range, you know it is a structure because it formed through a continuous process. Tectonic plates collided, rock folded, erosion carved valleys. It has geological coherence. It is one system. But what does it mean for something to be a structure when it is made of galaxies? When the individual components are themselves vast beyond comprehension? When the whole thing spans distances that light cannot cross within the current age of the universe? It means we have to look for coherence in a different way. We have to ask, do the parts move together? Do they share a common origin? Are they connected by physical processes? And the answer, surprisingly, is yes. The filaments of the cosmic web are not random. Galaxies within them share similar motions. They are all flowing along the filament, pulled by the combined gravity of all the matter within it. The filaments themselves are connected to nodes, to cluster points where matter accumulates, and these clusters affect the motion of galaxies across hundreds of millions of light years. This is physical coherence. This is structure in a real, measurable sense. But even within the cosmic web, even among these vast filaments and walls and voids, there are structures that stand out. Structures so large that they seem to represent the upper limit of what gravity can build before the expansion of the universe tears things apart. And this is where we arrive at the specific structure we need to discuss. The one that holds the title, for now, of the largest structure ever discovered in the universe. But I want you to understand what you are about to hear, because the name will not mean anything to you at first. It will just be words. What matters is understanding what it represents, what it tells us about the universe. This structure is a wall, not a wall like a wall in a room, a wall of galaxies, a continuous sheet of galaxies stretching across an almost incomprehensible expanse of space. It curves, it has thickness, it has regions that are more dense and regions that are less dense, but it is coherent. It is one structure. It is called the Hercules Corona Borealis Great Wall. The name comes from the region of sky where it was discovered, spanning the constellations Hercules and Corona Borealis as seen from Earth. But the structure itself is not in those constellations. It is far beyond them. It is so far away that the light we detect from it began its journey billions of years ago, when the universe was younger, when the galaxies in that wall were in different positions than they are now. The Hercules, Corona Borealis Great Wall spans approximately 10 billion light years across. 10 billion light years. Let me try to give you a sense of what this means, even though it will fail. Even though all attempts to make this comprehensible will fail. If you could somehow travel at the speed of light, the fastest possible speed in the universe, it would take you 10 billion years to cross from one end of this structure to the other. 10 billion years. The universe is 13.8 billion years old. This structure is nearly as wide as the universe is old. If you stood at one end and looked toward the other end, the light you would see coming from the far side would show you galaxies as they were 10 billion years ago. Those galaxies have aged 10 billion years since that light was emitted. They have changed. Stars have been born and died. Some of those galaxies may have merged with others. The structure has evolved, but you would not know that. You would only see the ancient light. You would be looking at a version of the structure that no longer exists in that form. This is what happens at extreme scale. The structure becomes smeared across time. You cannot see it all at once, in any meaningful sense, because a once stops being a coherent concept. There is no universal now when light takes billions of years to travel. The Hercules Corona Borealis Great Wall contains billions of galaxies. Each of those galaxies contains hundreds of billions of stars. Each of those stars may have planets, and the entire assembly, this incomprehensible collection of matter and light and gravity, forms one coherent structure. It was discovered through gamma ray bursts. These are some of the most energetic events in the universe, caused by the collapse of massive stars or the collision of neutron stars. When a gamma ray burst occurs, it releases more energy in a few seconds than the Sun will release in its entire 10 billion year lifetime. And these bursts are so bright that we can detect them from across the entire observable universe. Astronomers noticed that gamma ray bursts were not distributed evenly across the sky. There was a region where they clustered, a region where many more bursts were being detected than statistical chance would predict. This clustering suggested that there was an overdensity of galaxies in that region. More galaxies means more stars, which means more gamma ray bursts. By mapping the positions of these bursts, by measuring their distances using redshift data, astronomers were able to reconstruct the three-dimensional structure of the region. And what they found was this wall, this enormous concentration of matter stretching across 10 billion light years. At first, there was skepticism. Structures this large were not supposed to exist. There is a theoretical limit to how large structures can grow in the universe, based on the amount of time available since the Big Bang and the speed at which gravity can pull matter together. This limit is called the maximum structure size, and it is roughly 1.2 billion light years. The Hercules Corona Borealis Great Wall is about 8 times larger than this theoretical limit. This created a problem. Either the theory was wrong, or the structure was not real. Or, more subtly, the structure was real, but our definition of structure was too rigid. The current understanding is that the Great Wall is real, but it may not be a single, bound structure in the way a galaxy cluster is bound. It may instead be a statistical overdensity, a region where, by chance or by the specific conditions of the early universe, more matter ended up than in surrounding regions. The galaxies in it may not all be gravitationally bound to each other. They may be moving independently, but all happening to be in the same general region of space. This raises a philosophical question. If the parts are not bound together, is it really a structure? Or is it just a pattern we are imposing on the data? There is no clear answer, but here is what we can say with certainty. The Great Wall is a region of space where matter is organized in a non-random way across 10 billion light years. Whether we call it a structure, or a feature, or an overdensity, it represents the largest coherent arrangement of matter we have ever detected. And it is not alone. There are other Great Walls. The Sloan Great Wall, about 1.37 billion light years long. The CFA2 Great Wall, about 500 million light years long. These are smaller than the Hercules Corona Borealis Great Wall, but they are the same type of structure. Long, thin concentrations of galaxies stretching across the cosmic web. There are also supervoids. The Boötes void, a region about 330 million light years across that contains very few galaxies. The CMB cold spot, possibly associated with an even larger supervoid. These are the inverse of great walls. They are regions where matter has been evacuated, leaving behind vast expanses of nearly empty space. Together, the walls and the voids define the cosmic web. They are the largest scale structures in the universe, and they tell us something profound about how the universe works. They tell us that gravity, given enough time, will organize matter at every possible scale, from planets to stars to galaxies to clusters to superclusters to great walls. There is no scale at which gravity gives up and says, "This is large enough." It keeps working, keeps pulling, keeps building structure, until the expansion of the universe pulls things apart faster than gravity can pull them together. And this is the key to understanding the Great Wall. It exists at the boundary between structure and chaos. It is as large as structure can be before cosmic expansion wins. It represents the maximum reach of gravity in a universe that is accelerating apart. Because the universe is expanding. Not just expanding, but accelerating. The space between distant galaxies is growing faster and faster over time, driven by something we call dark energy. And this expansion is in direct competition with gravity, in regions where matter is dense. Where galaxies are close together, gravity wins. It pulls matter into clusters and holds them together. These clusters will survive. They will persist for trillions of years. But in regions where matter is spread thin, where the distances are too vast, expansion wins. It pulls things apart faster than gravity can pull them together. These regions will become voids. They will empty out. The galaxies in them will drift away from each other until they are so far apart that light from one can never reach another. The Great Wall exists in the middle. It is dense enough to have formed, but not dense enough to be permanent. It is not a bound structure. It will not hold together. Over time, the expansion of the universe will stretch it, thin it out, dissolve it into the expanding space around it. This is true of all the great walls, all the filaments of the cosmic web. They are temporary. They formed during a specific era of the universe's history, when matter was clumpy enough to create structure, but when the universe was not yet expanding so fast that structure formation became impossible. We live in that era now. We live in the age when the universe has the most structure it will ever have. Billions of years from now, the expansion will have erased the cosmic web. The great walls will be gone. The filaments will be gone. Even galaxy clusters will start to thin out, their member galaxies drifting apart. Eventually, in the far future, in trillions of years, each remaining galaxy will be alone in the observable universe, an island of light surrounded by darkness in all directions. The cosmic web will be a distant memory encoded in the motion of stars and the distribution of elements, but it will not be visible anymore. There will be no new astronomers in that future who could discover what we have discovered. They will look out and see nothing but their own galaxy and empty space, unless they are us. Unless they are the descendants of civilizations that recorded what the universe looked like when structure still existed. This is one of the gifts of living now. We live in an era when the universe is knowable, when we can look out and see the cosmic web, when we can detect great walls and measure their size and understand how they formed. But back to the structure itself. Back to the Hercules, Corona Borealis Great Wall. What is it like to exist in that structure? What would it be like to be on a planet in a galaxy that is part of that wall? You would not notice anything unusual. You would look up at the night sky and see stars, just like we do. You would see other galaxies, just like we do. You would not feel like you are part of a structure 10 billion light years across because you cannot perceive scale at that level. No one can. The The Great Wall is only visible as a structure when you zoom out. When you map millions of galaxies and look at their distribution. When you step back so far that individual galaxies become points of light and the overall pattern emerges. This is true of all cosmic structure. It is invisible from the inside. You have to zoom out to see it. And this raises a question. Are we part of a larger structure that we cannot see yet? Are there patterns in the universe at scales, even larger than the Great Wall, that we have not detected because we have not zoomed out far enough? Probably not. The observable universe has a limit. We can only see as far as light has had time to travel since the Big Bang, which is about 46.5 billion light years in any direction due to expansion. We have mapped most of the observable universe. We have found the cosmic web. We have found the Great Walls. If there were larger structures, we would see hints of them in the data. We would see asymmetries in the distribution of galaxies. We would see patterns that suggested something beyond the edge of the observable universe was influencing what we can see. We do not see that. The universe appears roughly the same in all directions at the largest scales. This is called the cosmological principle. It states that the universe, when averaged over large enough volumes, is homogeneous and isotropic. The same everywhere, the same in every direction. The Great Wall does not violate this principle because it is a local feature. It is large, but it is still much smaller than the observable universe. When you average over volumes larger than 10 billion light years, the Great Wall disappears into the statistics. It becomes noise. This tells us something important. The Great Wall is not a fundamental feature of the universe. It is an accident, a statistical fluctuation. It formed because the early universe had tiny variations in density, and those variations grew over time through gravity. In some regions, the variations happened to align in such a way that matter formed a long, thin wall. In other regions, the variations created clusters or voids. But there is nothing special about the wall itself. It is not designed. It is not required. It is just what happened in that particular region of space. And yet, it is the largest thing we have ever found, the largest coherent arrangement of matter in the known universe. This accident, this statistical fluctuation, is 10 billion light years across. What does this tell us about the universe? What does it tell us about ourselves? It tells us that the universe is bigger than we can comprehend, but not bigger than we can measure. It tells us that structure exists at every scale, from the quantum to the cosmic. It tells us that gravity is relentless, always pulling, always organizing, always building until something stronger, like cosmic expansion, stops it. And it tells us that we are very, very small, not small in a diminishing way, not small in a way that makes us insignificant, small in a way that is clarifying, small in a way that puts things in perspective. We live on a planet 8,000 miles wide. Our planet orbits a star in a galaxy 100,000 light years across. Our galaxy is part of a supercluster 500 million light years across. And that supercluster is part of a cosmic web that contains structures 10 billion light years across. At each step, the scale increases by factors of millions or billions. And yet at each step, the physics is the same. Gravity Potter clumps. Structure forms. The Great Wall is not made of exotic matter. It is not held together by mysterious forces. It is made of the same atoms that make up your body: hydrogen, helium, carbon, oxygen, iron, the same elements forged in the cores of stars and scattered into space when those stars died. The only difference is scale. The Great Wall is what happens when you take the same building blocks that make a planet and assemble them over 10 billion light years instead of 8,000 miles. This is the deep lesson of cosmology. The universe uses the same rules at every scale, the same forces, the same particles. There is no fundamentally new physics when you go from galaxies to Great Walls. There is only more space and more time for those forces to act. And this means that understanding the Great Wall is not fundamentally different from understanding a planet or a star. It is just harder, because the numbers are larger and because the timescales are longer. But the principles are the same. Gravity pulls matter together. Matter forms structures. Those structures evolve over time, and eventually, those structures dissolve when expansion or entropy or some other force pulls them apart. The Great Wall is in the middle of its life cycle right now. It has already formed. It is detectable. We can measure it, but it is not growing anymore. The expansion of the universe has already won at these scales. The Great Wall is not getting larger or more massive. It is, very slowly, beginning to disperse. In 100 billion years, it will be gone. The galaxies that make it up will still exist, many of them, but they will have drifted apart. The wall will have stretched and thinned until there is no statistical excess of galaxies in that region anymore. It will have dissolved into the background, and no one will know it was ever there unless they have records from our era, unless they have maps made by astronomers in the 21st century who looked out and measured the positions of millions of galaxies and found this pattern. This is the fate of all large-scale structure. It is temporary. It is a feature of this particular era in the universe's history. There was a time in the early universe when there were no structures at all, just a hot, dense soup of particles expanding and cooling. No stars, no galaxies, no great walls, just smooth, featureless matter filling space. Then gravity began to act on tiny fluctuations. Matter started to clump. The first stars formed. The first galaxies assembled. The cosmic web began to emerge. We live in the age of structure, the age when the universe is complex and interesting and full of patterns. But this age will end. In the far future, the universe will return to smoothness, not because matter will mix back together, but because expansion will have separated everything so far that the universe will be empty again, smooth again, featureless again. The Great Wall is a monument to this temporary age. It is the largest marker of the era when the universe was structured. And we are here to see it. We are here to measure it. We are here to understand it. There is something profound about this. We are living in the brief window of cosmic time when intelligence can emerge and look out and see the universe as it truly is. Before this era, there were no planets capable of supporting life. After this era, the universe will be too empty for anyone to discover its true nature. We are in the middle. We are in the age of knowability, and what we have discovered is that the universe builds structures at every scale it can, up to and including walls of galaxies 10 billion light years across. But now I want to return to the question of what large means, because we have been using numbers and distances, and those numbers are so extreme that they have stopped meaning anything. 10 billion light years is not a distance you can picture. It is not a distance you can feel. So let us think about it differently. Let us think about time. Light from the far side of the Great Wall has been traveling for 10 billion years. It left those distant galaxies when the universe was only about 3.8 billion years old. It has been crossing empty space ever since, moving at the maximum possible speed, and it is only now reaching us. During that journey, here is what happened on Earth. 10 billion years ago, Earth did not exist. The Sun did not exist. The solar system had not formed yet. There was just a cloud of gas and dust in the Milky Way, slowly collapsing under its own gravity. About 4.6 billion years ago, that cloud collapsed and the Sun ignited. Earth formed from the leftover material. At this point, light from the Great Wall was already halfway here. About 4 billion years ago, life began on Earth. Single-celled organisms in the ocean. Light from the Great Wall was still traveling. About 540 million years ago, complex life exploded into existence during the Cambrian period. Light from the Great Wall was in the final stretch of its journey, but still millions of light years away. About 65 million years ago, an asteroid struck Earth and wiped out the dinosaurs. Light from the Great Wall was very close now, just 65 million light years away. About 300,000 years ago, modern humans evolved in Africa. Light from the Great Wall was almost here. About 10,000 years ago, humans invented agriculture. Light from the Great Wall was 10,000 light years away, still crossing the Milky Way. In 1609, Galileo pointed a telescope at the sky for the first time. Light from the Great Wall was about 400 light years away. In 2013, astronomers analyzing gamma ray burst data discovered the Hercules Corona Borealis Great Wall. The light from the most distant parts of that structure had finally arrived. It had been traveling for 10 billion years, crossing an expanding universe, and it reached Earth just in time for us to build the instruments capable of detecting it. This is what large means in a cosmic sense. It means a structure so vast that light from it carries the history of the universe. It means a structure that spans not just space but time. When you look at the Great Wall, you are not seeing a thing. You are seeing a process. You are seeing gravity acting over billions of years to organize matter into patterns. You are seeing the universe writing its autobiography in the distribution of galaxies. And here is the truly unsettling part. We are part of that process. We are not observers standing outside the universe looking in. We are inside it. We are made of atoms that were forged in stars that are part of the cosmic web. We are matter that has organized itself into a form capable of understanding the organization of matter. The universe has become complex enough to study itself. And what it has discovered is that it builds structures 10 billion light years across. There is no purpose to this. No intention. The Great Wall did not form in order to be discovered. It formed because gravity pulls matter together and because the early universe had density fluctuations. That is all. And yet, here we are, capable of detecting it, capable of measuring it, capable of understanding, at least in principle, how it formed and why it exists. This is the gift of intelligence. Not that it makes us special, not that it gives us dominion over the universe, but that it allows us to see, to understand, to know that we are part of something larger. And the Great Wall is the largest thing we are part of, the largest structure in the cosmic web, the largest arrangement of matter we have ever found. But it is not the limit. It cannot be, because the observable universe is just the part we can see. Beyond the edge of our observations, the universe continues. It may be infinite. It may contain structures even larger than the Great Wall. We will never know. The speed of light and the expansion of the universe guarantee that there are regions of space we will never be able to see, even in principle. Light from those regions will never reach us because the space between us and them is expanding faster than light can cross it. This is called the cosmological horizon. It is the ultimate limit of knowability. Beyond it, the universe exists, but we cannot observe it. We cannot measure it. We cannot include it in our maps. And so the Hercules Corona Borealis Great Wall holds the title of largest structure, but only with an asterisk. Only within the observable universe. Only among the things we can actually detect. There may be larger structures beyond the horizon. There may be patterns we cannot see, but they are beyond our reach. They are unknowable, and perhaps that is fitting. Perhaps it is appropriate that the universe has secrets, that there are scales even larger than what we can measure, that no matter how much we learn, there is always more beyond the edge of our knowledge. The Great Wall reminds us of this. It sits near the edge of the observable universe, near the boundary of what we can detect. It is almost at the limit, almost beyond reach, and it makes us wonder what else is out there. What other structures exist in regions we will never see? What patterns have formed in the parts of the universe that are forever hidden from us? We will never know, but we can imagine. And in imagining, we can appreciate the vastness of what we are part of. Because even if the Great Wall is not the largest structure in the entire universe, it is the largest structure we will ever confirm. It represents the boundary of human knowledge at the largest scales. It is the furthest we can push our understanding of cosmic structure. And that is enough. That is more than enough. To live in an era when we can detect structures 10 billion light years across. to have the technology and the knowledge and the curiosity to map the universe at these scales, to be able to say with confidence that we have found the cosmic web and measured its largest features. This is a privilege, a cosmic privilege. We live in the narrow window of time when this is possible. Before us, no human knew these structures existed. After us, humans will know, but only because we recorded it. Only because we made the measurements and created the maps and wrote down what we found. The Great Wall will outlive us by billions of years, but it will not outlive the universe. Eventually, even structures this vast dissolve. Eventually, expansion wins. And this brings us to a deeper understanding of what we have discovered. The Great Wall is not just the largest structure in terms of size. It is also one of the most ephemeral when you consider its lifespan relative to its formation time. Think about this paradox. The Great Wall took billions of years to form. It required countless generations of stars to live and die, creating the heavy elements that make up planets and life. It required dark matter to provide the gravitational scaffolding. It required normal matter to flow along that scaffolding, clustering into galaxies. It required those galaxies to organize themselves into filaments and sheets. All of this took time, enormous amounts of time. The Great Wall is, in a sense, older than most of the stars we can see in the night sky. It is a relic of processes that began when the universe was young. And yet it is already beginning to fade, not in the sense that it is disappearing right now, this instant, but in the sense that its fate is sealed. The expansion of the universe is accelerating, driven by dark energy, and this acceleration means that large-scale structures will not survive indefinitely. The Great Wall formed during a special epoch in cosmic history, an epoch when the universe was old enough for gravity to have assembled large structures, but young enough that expansion had not yet torn everything apart. We happen to live during this epoch. We are witnessing the universe at peak structure. In the future, when expansion has had more time to work, the cosmic web will dissolve. The Great Wall will spread out, its galaxies separating from each other until they are no longer recognizable as part of a single structure. And new observers, if they exist, will look out and see a much emptier universe. They will not be able to discover what we have discovered. They will not be able to measure the Great Wall because it will no longer exist as a measurable structure. They will have to rely on ancient records, on data preserved from our era, to know that the universe once looked like this. This is a sobering thought. The universe is not static. It is not eternal in its current form. It is evolving, changing, moving toward a future that is fundamentally different from the present. And we are living in one of the most interesting moments of that evolution. We are living when the universe is at its most complex, its most structured, its most diverse. The Great Wall is evidence of this complexity. It is a snapshot of the universe at a moment when structure was possible at the largest scales, a moment that will not last. But let us dig deeper into what the Great Wall actually tells us about the physics of the universe. Because discovering it was not just about finding something large. It was about testing our theories, about confirming or challenging what we thought we knew. When the Great Wall was first detected, it created a crisis in cosmology. Not a crisis in the sense of overturning everything we knew, but a crisis in the sense of forcing us to reconsider some of our assumptions. The problem was the cosmological principle. This is the idea that the universe, when viewed at large enough scales, should be homogeneous, the same in all directions, no special locations, no preferred structures. But the Great Wall seemed to violate this. Here was a structure 10 billion light years across. How could the universe be homogeneous if it contained structures this large? The resolution came from understanding what large enough scales means. The cosmological principle does not say that the universe is smooth at all scales. It says that if you average over large enough volumes, the universe becomes smooth. And large enough turns out to be larger than 10 billion light years. When you look at the universe on scales of tens of billions of light years, the Great Wall disappears. It becomes just one feature among many. The overall distribution of matter becomes smooth again. This is similar to looking at a beach. Up close, you see individual grains of sand. The beach looks rough, uneven, grainy. But from far enough away, the beach looks smooth. The individual grains disappear into a uniform color. The Great Wall is a grain of sand on the cosmic beach. It looks huge when you are close to it, when it fills your field of view. But when you zoom out far enough, it is just one ripple among many. This tells us something important about scale and structure. It tells us that the universe has structure at every scale we have looked at, but it also tells us that there is a scale at which structure stops, a scale at which the universe becomes smooth. We have not reached that scale yet in our observations. We can only see out to the edge of the observable universe, and at that distance, we are still seeing structure. We are still seeing the cosmic web, but we believe, based on theory and on measurements of the cosmic microwave background, that if we could see further, we would eventually reach a scale where the universe is smooth, where all the structure averages out, where the cosmological principle holds perfectly. The Great Wall exists in the realm where the universe is still lumpy, where structure is still visible, but it is near the upper limit of that realm. It is one of the largest lumps. And this makes it valuable scientifically, because by measuring the Great Wall, by understanding its properties, we can test our models of how structure forms in the universe. Those models depend on several key ingredients. Dark matter, which provides most of the gravitational pull. Dark energy, which drives the acceleration of expansion. The initial density fluctuations from the early universe, which seed structure formation. And the ordinary matter, the atoms and molecules and stars and galaxies that we can actually see. All of these ingredients have to work together in precise ways to produce the cosmic web we observe. And the Great Wall is a test case. If our models can predict structures this large, if they can explain why the Great Wall formed where it did and when it did, then we have confidence that our models are correct. And they do. The models predict that structures like the Great Wall should exist, not in every region of space, but in some regions, as statistical outliers, as rare but not impossible arrangements of matter. The Great Wall is rare, but it is not unique, and that is important. If it were unique, if it were the only structure of its kind, that would suggest something special about it, something that required explanation beyond our standard models. But it is not unique. There are other Great Walls, smaller but similar. There are other large-scale structures. The Great Wall is just the largest example of a type of structure that is predicted by our models. This confirmation is reassuring. It tells us that we understand, at least roughly, how the universe works at the largest scales. We understand how gravity and expansion compete. We understand how structure forms and evolves. We understand why the universe looks the way it does. But there are still mysteries, still questions that the Great Wall raises. One of those questions is about the initial conditions of the universe, the density fluctuations that seeded structure formation. Where did they come from? Why did they have the specific pattern they had? The leading theory is cosmic inflation. This is the idea that the universe, in its first fraction of a second, expanded exponentially, and this expansion stretched quantum fluctuations in the fabric of space to macroscopic scales. These stretched quantum fluctuations became the density variations that gravity later amplified into stars, galaxies, and Great Walls. If this theory is correct, then the Great Wall is a direct descendant of quantum mechanics. It is a macroscopic imprint of processes that occurred at the smallest possible scales, at the earliest possible moments after the Big Bang. This is a beautiful connection. It links the largest structures in the universe to the smallest processes in physics. It suggests that the universe is unified, that the same laws apply everywhere and at all times. But we do not know for certain that inflation happened. We have evidence that supports it. We have measurements of the cosmic microwave background that match the predictions of inflation. But we do not have direct proof. The Great Wall, and structures like it, are indirect evidence. They are the outcomes of processes that inflation would have set in motion. By studying them, we are studying the consequences of inflation, even if we cannot observe inflation directly. And this is often how science works. We cannot always observe the processes we are interested in, but we can observe their effects. We can measure the outcomes, and from those outcomes, we can infer what must have happened. The Great Wall is an outcome. It is the result of billions of years of gravity acting on matter. But it is also, indirectly, a window into the first moments of the universe, into the processes that set everything in motion. This is one of the reasons why cosmology is so compelling. It connects the largest and the smallest, the oldest and the youngest, the visible and the invisible. When we look at the Great Wall, we are not just seeing galaxies. We are seeing history. We are seeing the story of how the universe evolved from a smooth, featureless state to the complex, structured cosmos we observe today. And that story is written in the distribution of matter, in the positions and motions of galaxies, in the shapes and sizes of structures like the Great Wall. Reading that story requires patience. It requires careful measurements. It requires sophisticated instruments and years of observations. But the story is there, and we have read it, and what it tells us is that the universe started simple and became complex. That structure emerged from smoothness. That order arose from chaos. The Great Wall is a chapter in that story, a chapter about the largest scales, about what happens when gravity has billions of years and billions of light years to work with. And the chapter is still being written. The Great Wall is still evolving, slowly, imperceptibly, but continuously. Galaxies are still moving. Stars are still being born and dying. The structure is still changing. We have captured a snapshot, a moment in the life of the Great Wall. But that moment is not static. It is a frame in a much longer movie. If we could watch that movie, if we could see the Great Wall evolve over billions of years, what would we see? We would see it form first. We would see galaxies, initially scattered randomly, begin to cluster, begin to flow toward regions of higher density, begin to organize themselves into filaments and sheets. This would happen slowly. So slowly that even if you watched for 1,000,000 years, you would barely notice the change. But over hundreds of millions of years, the pattern would emerge. The galaxies would spread themselves out along the filaments, creating the structure we see today. And then, if we kept watching, we would see it begin to fade. We would see the expansion of the universe take over. We would see the galaxies drift apart, the filaments stretch and thin, the structure dissolve. This would also happen slowly, billions of years, trillions of years. But eventually, the Great Wall would be gone. The galaxies that made it up would still exist, many of them, but they would no longer be part of a coherent structure. This is the fate of the Great Wall. This is the future we can predict with confidence based on our understanding of cosmology. But there is a twist, a complication that makes the future less certain than it might seem. Dark energy, the mysterious force that is accelerating the expansion of the universe. We know dark energy exists. We have measured its effects. We know it is causing the universe to expand faster and faster over time. But we do not know what it is. We do not know if it is constant or if it is changing. We do not know if it will continue forever or if it will eventually stop or reverse. And this uncertainty affects our predictions about the future. Because if dark energy remains constant, the future I described, where the Great Wall dissolves and the universe becomes empty, is what will happen. But if dark energy changes, the future could be different. If dark energy gets stronger, the universe could expand so fast that even galaxies tear apart, even stars, even atoms. This is called the Big Rip, and it would bring a violent end to everything. If dark energy weakens or reverses, the universe could stop expanding and start contracting. gravity could pull everything back together, eventually leading to a big crunch, a reverse of the Big Bang. We do not know which of these futures awaits us. We do not know because we do not understand dark energy well enough. And the Great Wall, as the largest structure in the universe, is sensitive to this uncertainty. Its future depends on what dark energy does. If dark energy remains constant, the Great Wall has billions of years left, trillions of years perhaps before it completely dissolves. If dark energy strengthens, the Great Wall might not last that long. It might tear apart sooner, much sooner. If dark energy weakens, the Great Wall might last longer. It might even survive until the universe starts contracting, at which point it would begin to collapse, pulling galaxies back together instead of letting them drift apart. All of these futures are possible. All depend on the nature of dark energy, which is one of the biggest unsolved mysteries in physics. The Great Wall is a witness to this mystery. It exists in a universe dominated by dark energy. Its fate is tied to the fate of dark energy. By studying it, by measuring its evolution, we might learn something about what dark energy is and what it will do. This is another reason why the Great Wall is scientifically important. It is not just a curiosity, it is a laboratory, a natural experiment in cosmology. By watching how the Great Wall changes over time, by measuring the motions of galaxies within it, by tracking how it responds to the expansion of the universe, we can test our theories about dark energy. Of course, watching over time means something different in cosmology than it does in everyday life. We cannot literally watch the Great Wall change. It changes too slowly. Even over a human lifetime, even over many human lifetimes, the changes would be imperceptible. But we can measure galaxies at different distances, which means we are seeing them at different times in the past. By comparing galaxies that are closer to us, and therefore seen as they were more recently, to galaxies that are further away, and therefore seen as they were longer ago, we can reconstruct how structures like the Great Wall have evolved. This is how we do time, lapse photography in cosmology. We do not watch one object change. We compare many objects at different stages of their evolution. And what we have learned is that structures like the Great Wall have been growing for most of the history of the universe. Gravity has been pulling matter together, making the structures denser and more defined. But there is evidence that this growth has been slowing down. That in the recent history of the universe, in the last few billion years, dark energy has become dominant. And now, instead of structures growing, they are beginning to freeze in place. They are not getting denser anymore. They are just sitting there while the space around them expands. The Great Wall is at this transition point. It formed during the era when structure growth was still happening, but it exists in an era when growth has mostly stopped. It is a structure caught between two epochs, between the era of growth and the era of expansion. This makes it a fossil, a relic of a time when the universe was still actively building structures, a time that is now coming to an end. In the future, new great walls will not form. The universe will be expanding too fast. Gravity will not be able to pull matter together at these scales anymore. The great walls that exist now, including the Hercules, Corona Borealis Great Wall, are the last of their kind. They are the final generation of large-scale structures. And we are here to see them. We are living in the last era when structures this large exist. After us, after our descendants, after countless future generations, the universe will be different, emptier, less structured. The Great Wall will be a memory, a footnote in the history of the universe, a brief moment when matter organized itself at the largest possible scales. But for now, it exists, and we can measure it. And in measuring it, we can understand something profound about the universe and our place in it. We can understand that we live in a special time, a time when the universe is complex enough to support life, but structured enough to be interesting. A time when intelligence can emerge and look out and see the cosmos in all its glory. This is not a permanent state. The universe was not always like this, and it will not always be like this, but it is like this now, and that is enough. The Great Wall exists now. We exist now, and we have found each other across 10 billion light years, across billions of years of cosmic history. This meeting, this discovery, is itself a kind of structure, a connection between matter that has organized itself into galaxies and matter that has organized itself into minds. Both are temporary, both will dissolve eventually, but both are real, both exist, both matter. The Great Wall matters because it is the largest structure in the universe, because it tells us about the limits of what gravity can build, because it tests our theories and challenges our assumptions. But it also matters because it reminds us of something essential about existence, that everything is temporary, that even the largest structures dissolve, that nothing lasts forever. This is not a depressing realization, it is a clarifying one, because if nothing lasts forever, then the time we have matters more. The structures we build, the knowledge we create, the connections we make, all of these things are precious precisely because they are temporary. The Great Wall will not last forever, but it exists now, and we have discovered it. And that discovery, that moment of understanding, that connection between human minds and cosmic structure, is something that happened. It is part of the history of the universe now, even if the universe will eventually forget. We cannot make things permanent. We cannot stop the expansion of the universe or reverse the flow of entropy or prevent structures from dissolving. But we can witness, we can measure, we can understand, and we can record. We can make maps of the Great Wall. We can write papers about it. We can share our knowledge with others. We can pass it down to future generations. And in doing so, we extend the life of the Great Wall in a sense. Not the physical structure, but the knowledge of it, the understanding of it, the awareness that it exists. As long as beings remember the Great Wall, as long as records survive, the Great Wall lives on in minds and databases and archives, not as a physical structure, but as an idea, as knowledge. This is the gift we can give to the future, the gift of knowledge about the universe as it was during our era, during the age of structure. Future beings, if they exist, will live in a different universe, an emptier universe, a universe where the cosmic web has dissolved and the Great Walls are gone. But they will be able to know what the universe looked like in our time. They will be able to see our maps and our measurements and our photographs. They will be able to understand that the universe was once filled with structure at the largest scales. And they will know that we were here, that we looked out and saw the Great Wall and measured it and understood it. This is a kind of immortality, not for us as individuals. We will die. Our civilizations will eventually end. Even our species will go extinct someday. But our knowledge can survive. Our discoveries can outlive us. The Great Wall, as a physical structure, will dissolve. But the Great Wall, as a piece of human knowledge, can persist as long as there are beings to remember it. This is why we do science. Not just to satisfy curiosity, though that is part of it, but also to create something lasting. To add to the sum of knowledge that civilization can pass forward. The Great Wall is our discovery, our contribution to that sum, our addition to the map of the universe. And it is a worthy addition, because the Great Wall is not just large, it is the largest. It represents the boundary of what structure can be in this universe. It is the upper limit, and we found it. We measured it. We understood it. This is what humans can do. This is what intelligence can achieve. We can take the universe, vast and incomprehensible, and make it comprehensible. We can measure what seems unmeasurable. We can understand what seems beyond understanding. The Great Wall spans 10 billion light years. That distance is beyond human intuition, beyond human experience, beyond anything we evolved to deal with. And yet we have dealt with it. We have developed mathematics that can handle numbers this large. We have built instruments that can detect light from distances this vast. We have created theories that can explain how structures this large form and evolve. We have taken something that should be beyond us and brought it within reach. Not physical reach. We will never travel to the Great Wall. We will never see it up close. But intellectual reach, mental reach, we have reached across 10 billion light years with our minds and grasped what is there. This is the true power of intelligence, not physical strength, not size, not longevity, but the ability to transcend our limitations through understanding. We are small, the Great Wall is large, but we understand it, and it does not understand us. In that sense, we have a kind of power over it, not the power to change it or control it or destroy it, but the power to know it, to comprehend it, to include it in our models of reality. And that power, the power of knowledge, is the only power that really matters in the end, because physical power is temporary. Physical structures dissolve, physical beings die, but knowledge can propagate, ideas can spread, understanding can be shared and preserved and built upon. The Great Wall is the largest structure, but the knowledge of the Great Wall is potentially unlimited in how far it can spread, how long it can last, how many minds it can touch. We discovered the Great Wall in 2013, just over a decade ago as I speak. This knowledge is young. It has only just entered human consciousness, but it can spread, it can be taught, it can be shared. Every person who learns about the Great Wall expands the reach of this knowledge. And every person who understands the Great Wall, who grasps what it means, who appreciates its significance, is participating in something profound. They are participating in the universe's process of understanding itself. Because that is what we are. We are how the universe understands itself. We are arrangements of atoms that have become complex enough to think about arrangements of atoms. The Great Wall is an arrangement of atoms at the largest scale. We are an arrangement of atoms at a much smaller scale, but we are connected. We are part of the same universe, made of the same matter, subject to the same laws, and we have found each other. The small has discovered the large. The simple has comprehended the complex. The temporary has measured the nearly eternal. This is remarkable. This is worthy of attention. This is something to be celebrated and preserved and shared. The Hercules Corona Borealis Great Wall, 10 billion light years across, billions of galaxies, the largest structure in the known universe, temporary, like everything else, like us, but real, existing now, measurable, understandable, and understood by us in this era. During this brief window when both we and the Great Wall exist, we are witnesses to something that will not last, but we are witnesses nonetheless. And our witnessing matters. It matters because witnessing is what consciousness does. It is our function in the universe, to observe, to measure, to understand. The Great Wall would exist whether we observed it or not, but by observing it, we have added meaning to its existence. We have connected it to the network of human knowledge. We have made it part of our story, and in doing so, we have made it part of something larger than itself, because human knowledge is a structure too, not a physical structure made of galaxies and stars, but an informational structure made of ideas and understanding. And that structure, that network of knowledge, is growing. It is connecting. It is becoming more complex. The discovery of the Great Wall is a node in that network, a point where cosmology and physics and mathematics and observation all come together, a place where our understanding of the universe deepens, and from that node, connections radiate outward, to other discoveries, to other ideas, to other minds. The Great Wall is not isolated in our knowledge any more than it is isolated in space. It is connected, part of a web, part of the larger structure of human understanding. And that web, that structure of knowledge, is perhaps the most important structure we have created, more important than buildings or cities or civilizations, because knowledge can survive when physical structures fall. Knowledge can rebuild what is lost. Knowledge can propagate across time and space in ways that matter cannot. The Great Wall is matter organized by gravity over billions of years. Human knowledge is information organized by minds over thousands of years. Both are structures. Both are remarkable. Both are temporary. But while the Great Wall's fate is sealed, while we know it will dissolve as the universe expands, the fate of human knowledge is uncertain. It depends on us, on what we choose to preserve, on what we choose to share, on whether we can maintain the continuity of civilization and understanding across the generations. This is a responsibility. The knowledge we have gained about the universe, about structures like the Great Wall, is precious. It took centuries of work to acquire. It represents the collective effort of thousands of scientists, each building on the work of those who came before, and it can be lost. Libraries can burn. Data can be destroyed. Civilizations can collapse. Knowledge that took centuries to build can disappear in a generation if it is not preserved and transmitted. The Great Wall will outlast human civilization, almost certainly. It will exist for billions of years. But the knowledge of the Great Wall is more fragile. It exists only in minds and in records, and both can be destroyed. This is why documentation matters, why education matters, why communication matters. We have discovered something profound about the universe, and that discovery is worth preserving, worth sharing, worth passing on to those who come after us, because they will live in a universe we cannot see, a future universe where the Great Wall may have already begun to fade, where the cosmic web may be dissolving, where the structures we can observe now may be harder to detect or gone entirely, and they will need our records, our measurements, our maps, to know what the universe looked like during our era, to understand the history of cosmic structure, to appreciate what they have lost and what we were privileged to witness. We are the generation that discovered the largest structure in the universe, that measured it, that understood it, that lived during the age when it existed in its full glory. This is our legacy. This is what we can pass forward, not the Great Wall itself, which will outlive us regardless, but the knowledge of it, the understanding of it, the awareness that it exists and what it means. And that legacy is worth protecting, worth preserving, worth ensuring that it reaches the future intact. Because the Great Wall is not just a collection of galaxies. It is a testament, a demonstration of what the universe can build when gravity has enough time and space to work, a marker of the limits of structure in an expanding cosmos. And our discovery of it is a testament too, a demonstration of what minds can achieve when they look outward, when they ask questions, when they refuse to accept ignorance about the universe they inhabit. The Great Wall exists at the edge of the observable universe, at the boundary of what we can detect. And our discovery of it exists at the edge of what we can understand, at the boundary of human knowledge. Both boundaries are expanding. Both can be pushed further, but both have limits. The observable universe has a horizon, a distance beyond which we cannot see, and human understanding has horizons too, limits to what we can comprehend, what we can measure, what we can know. The Great Wall sits near both horizons, near the edge of observation, near the edge of comprehension. It is almost beyond our reach in both senses, but not quite. We can just barely detect it. We can just barely understand it. It is at the limit, but within the limit. And that makes it precious, because it represents what we can achieve when we push ourselves to the edge. When we refuse to stop at the comfortable, the familiar, the easily understood, the Great Wall challenges us. It forces us to think at scales that hurt, to consider numbers that feel meaningless, to accept that the universe is larger and stranger than our intuitions suggest. And in rising to that challenge, in accepting that discomfort, we grow. We expand our understanding. We push our horizons a little further out. This is what the discovery of the Great Wall represents. Not just a measurement, not just a data point, but an expansion of human knowledge, a step toward a more complete understanding of the universe. And every step matters. Every discovery builds on the last. Every expansion of knowledge makes the next expansion possible. The Great Wall was discovered because we built better telescopes, because we developed new analysis techniques, because we asked new questions, because we looked where no one had looked before. And now that we know it exists, we can ask new questions. We can make new measurements. We can push our understanding even further. What other structures exist at these scales? How do they form? How do they evolve? What do they tell us about the fundamental nature of the universe? These questions have answers, and we can find them by continuing to observe, by continuing to measure, by continuing to think. The Great Wall is not the end of discovery. It is a waypoint, a marker on the path toward deeper understanding, a sign that we are on the right track, that our methods work, that we can know the universe at the largest scales. And knowing that we can know is itself valuable, because it gives us confidence, it gives us direction, it gives us reason to continue. The universe is vast. The Great Wall is vast, but vastness is not an obstacle to understanding. It is a challenge, an invitation, a promise that there is more to discover, more to learn, more to understand. And we are accepting that invitation. We are taking up that challenge. We are building on the discovery of the Great Wall, using it as a foundation for further exploration. Because the Great Wall, for all its size, is just one structure in a universe full of structure. It is the largest we have found, but it is not the only thing worth finding. It is not the only thing worth understanding. The universe contains multitudes, planets and stars and galaxies and clusters and superclusters and walls and voids. Each is worth studying. Each has something to teach us. Each adds to our understanding of how the universe works. The Great Wall is special because it is the largest, because it pushes the boundaries of what structure can be, because it tests our theories at the most extreme scales. But it is also representative. It is part of the cosmic web, part of the larger pattern of structure formation, part of the story of how the universe evolved from simplicity to complexity. And that story is what we are really after. Not just individual facts about individual structures, but the overarching narrative, the deep principles that explain everything. The Great Wall is a chapter in that story, an important chapter, but not the whole story. The whole story spans from the Big Bang to the heat death of the universe. From the first quantum fluctuations to the last black hole evaporating into nothing. From the formation of the first atoms to the dissolution of the last structures. And we are in the middle of that story, living during the age of complexity, the age of structure, the age when the universe is at its most interesting. The Great Wall is a product of this age. It could not have formed earlier, when the universe was too young and too small. It cannot form later, when the universe will be too expanded and too dominated by dark energy. It exists now, we exist now, and we have found each other. This meeting, this discovery, this moment of understanding is part of the story too. Part of the chapter about intelligence, about how the universe became capable of understanding itself. Because that is what has happened here. The universe, through us, has discovered the Great Wall, has measured it, has understood it, has incorporated it into the growing map of cosmic knowledge. And that map, that understanding, is itself a structure. One of the most remarkable structures in the universe, not because of its size, not because of its physical extent, but because of what it represents. It represents the transformation of matter into meaning, of particles into thoughts, of chaos into understanding. This transformation is what consciousness does. It is what intelligence achieves. It takes the raw data of the universe and processes it, organizes it, makes sense of it. The Great Wall is raw data, billions of galaxies arranged in space. Until we discovered it, until we measured it, until we understood what it was just there. Existing but unknown, real but unmapped. Now it is mapped, it is understood. And that transformation from unknown to known is as significant as any physical transformation in the universe. Because knowledge changes things, not physical things necessarily. The Great Wall is unchanged by our knowledge of it. It does not care that we have discovered it. But we are changed. Our understanding is changed. Our map of the universe is changed. And through us, the universe's understanding of itself is changed. This is the miracle of consciousness. This is the power of intelligence. To take a universe full of matter and energy and transform it, through observation and thought, into a universe full of meaning and understanding. The Great Wall is matter and energy organized by gravity. We are matter and energy organized by evolution. And together, through the process of discovery, we create something new, something that did not exist before, understanding. And that understanding, once created, cannot be uncreated. It can be lost if records are destroyed and memories fade, but it cannot be unmade. It happened. We discovered the Great Wall. We understood it. That is part of history now, part of the story of the universe. And it is a story worth telling, worth preserving, worth celebrating, because in a universe that is mostly empty, mostly dark, mostly cold, we have found beauty. In a universe that is mostly chaos, we have found order. In a universe that is mostly meaningless, we have created meaning. The Great Wall does not have meaning in itself. It is just galaxies arranged in space. But to us, it means something. It represents the limits of structure, the power of gravity, the story of cosmic evolution, the achievement of human discovery. And that meaning, that significance is real. Not in the sense that the Great Wall cares about it, but in the sense that we care about it, that it matters to us, that it changes how we see ourselves and our place in the cosmos. This is what the discovery of the Hercules, Corona Borealis Great Wall gives us. Not just a fact, not just a measurement, but a shift in perspective, a change in understanding, a deeper appreciation for the universe and our ability to comprehend it. We are small, the Great Wall is large, but through understanding, we bridge that gap. We connect across scales. We make the large comprehensible through thought. This is our power. This is our gift. This is what makes us significant despite our size. Not because we are large, not because we are powerful, not because we are eternal, but because we understand, because we can look at something 10 billion light years across and say, I know what that is. I know how it formed. I know what it means. This is the achievement. This is the triumph. This is what matters. The Great Wall will dissolve. We will die. The universe will expand and cool and empty out. But the understanding we have created, the knowledge we have built, the meaning we have found, these things have value that transcends their temporary existence. They have value because they happened, because they were real, because for a moment, in the vast expanse of space and time, matter organized itself into minds that could comprehend matter organized into structures. The Hercules, Corona Borealis Great Wall, the largest structure in the universe, 10 billion light years across, temporary, remarkable, and finally understood.